Okay, so we left off where we're going to decide on the entering arc, which is what we'll focus on now, based on reducing costs. Now, normally what we would then do is we would write, we don't know how to do that on the graph, so what we would do is we would write the LP, and then use the same LP method to identify the entering variable, and while we're at it, we might as well solve this whole problem with LP. So the people who were devising these algorithms started thinking, and let's just see let's compare what happens in the primal and in the dual. Suppose that we had then a primal formulation, primal model, which will be the original problem, which is to minimize. So it'll be minimize subject to greater than or equal to constraints. And then we could have also a dual model, which would be maximize subject to generally less than or equal to constraints. If you remember, when we go from, if it's equality, then the dual variables will be URS, but we will only have less than or equal to constraints, I believe. So suppose that in this particular case, the way the algorithm works is that we try to minimize. So this will be, let's say, the optimum, and we start at some initial basic feasible solution, and then we move down to another one, then out to another one, out to another one. At all times, the solutions will be basic and feasible. So we'll move down. This will no longer be initial. So I think we can remove this initial. It's understood that we're going from basic feasible solution. We'll start with 1, then we'll go with 2, 3, whatever it is, and we're making our way down. We're minimizing. Now, it is possible for every basic feasible solution, there's a corresponding dual. But the dual will be basic, but it will not be feasible. So there will be a dual basic infeasible, and in fact there will be super optimal. So here we're maximizing, but all we're doing here is we're translating this initial basic any basic feasible solution in the primal has a corresponding basic infeasible super optimal solution. Okay, so it's basic infeasible super optimal solution. Okay, BIS. And there will be one there, and then there will be, and this will move to a basic, another one super optimal, and this will be coming down, because what we're doing is we're increasing feasibility, and at the end it'll be basic, feasible, and optimal, and that's where these two are the same. So they're going to arrive at the same solution. Both of them are going to arrive at the optimal, but this is the dual simplex. So a dual simplex has the optimality condition maintained at all times, and this is the regular simplex. This is the primal simplex. This is just the regular simplex. This is the dual simplex. So what the researchers realized is that to move in the dual world is more computationally efficient than to move in the primal world. And that is the reason why the next thing we'll do is we'll formulate the primal and the dual models, and we'll see how to obtain for every basic feasible solution in the primal, how do we obtain the corresponding basic infeasible superoptimal solution in the dual. and then how do we go about increasing feasibility. So that's where we're going.